Okay, then it's my great pleasure to introduce Sasha Kyriienko, professor in the University of Exeter, working on many things quantum, but also recently working a lot in the quantum machine learning side of things. And in the talk today, he will tell us some recent results from his group, going from like scientific quantum machine learning, quantum scientific machine learning, and getting all the way to generative modeling. The floor is all yours. Take it away.
Yeah, thank you very much, Elise, and thank you for inviting to give this talk. It would be very big pleasure to visit Berlin one day, and specifically a few, but I'm happy that we arranged it for the QML seminar. So I thought about the subject, and we've been discussing the quantum embeddings for some time already. So my idea is to motivate how we progress from using embeddings for simple machine learning models, making them more complex, and finally, how can we use them for tasks in generative modeling. So we know that quantum computers nowadays are growing in size. They become more complicated, and at this point, we are already reaching the error correction thresholds. So the natural question is, what can we do useful with these devices? It turns out it's kind of challenging for limited budget and a smaller number of qubits that you could solve some practical problems. Yet, I believe I'm physicist, but my background is theoretical physics. I came to quantum computing from the quantum optics side. So for me, it's very important to consider something practical and see whether it may potentially work in the future. And when I think in terms of the future of quantum computing, that should be related to applications. So we need to understand where those devices will be applied. And big motivation is, of course, in anything that's related to physics and chemistry, but we can also try to solve problems in optimization. So the nice stream of works there. And specific area that me and my group were concentrating on is quantum machine learning and quantum scientific machine learning. So where we say, let's try to solve challenges of scientific computing using machine learning approaches on quantum devices. And as a substrip of quantum scientific machine learning, I see generative modeling. It will not be a ChatGPT style, but rather how can we sample from quantum models and solve stochastic differential equations, which in the future can be potentially connected to generative modeling in the general sense. So when we started to work in quantum scientific machine learning, we have concentrated on the differentiable quantum circuits. So in this case, you have what is also known as quantum neural network, even though it's not exactly the neural net. You just have a parameterized quantum circuit where there is a feature map, a circuit that takes X as a variable you would like to embed and prepares some quantum state. Then you do the variational quantum circuit that adjusts the measurement and builds the model f of x. So as long as we can measure f of x as a scalar, supply x through rotations and adjust the measurement, we have a latent space function, and we can ask, what do we do with that function? There is a large body of work solving problems in, let's say, classification. There are works on regression. And from that point, I have asked the question, so if we can differentiate quantum models with respect to variational parameters theta and adjust those, for instance, via parameter shift rule, why don't we also differentiate with respect to x as an embedding variable? This can be done, and in fact, if I have access to derivatives of my models, higher order derivatives, and the model itself, I can build physics-informed quantum neural networks. And at this point, I didn't really rely on the classical body of work in physics-informed neural network, but rather asking what is available for quantum. So we have tried this approach, and the important message there was quantum models formulated as expectations of observables are nonlinear with respect to, so I can easily encode nonlinearity. We can solve systems of differential equations. We could do a lot of things. So one example that we've tried was solving the quasi-1D version of Navier-Stokes equations and getting solutions with these physics-informed networks. And we also tried the kernel-based solvers for regression and differential equations, which would avoid non-convex optimization for certain systems. So that was one rather example that you can solve problems. And you could even go to the quantum model discovery stream, where instead of just using differential equations and boundary conditions, you could supply data and you could rediscover systems of differential equations and terms that represent this data. So that becomes much closer to classical machine learning and how pins are used. And that's a stream of research we've been doing together with Pascal. So initially it was Kyriienko with Vincent Elfin and Annie Payne, who just graduated from Exeter and joined Pascal as a researcher. So that was a story about scientific machine learning and just saying quantum circuits can do something for SciML. But the natural question appears, where is the power of quantum machine learning? Where does it come from? And the typical mantra we needed to say, it's processing data in the high-dimensional Hilbert space. So that's believed to be the main advantage of QNNs. But where does it come exactly? Over the time, we started to ask more and more questions. What's the regimes that you get advantage? And if I try to analyze quantum models, that's the beautiful work that appeared from Maria Schuld and colleagues, trying to understand what are the models that we built, how do they look like if you expand it in, for instance, Fourier series. And turns out that reuploading many layers of unitaries with interleaved coefficients, you could decompose it in spectrally. You could link together the unitaries, and you will see that f of x as a function of theta in the end will look like a bunch of Fourier harmonics. So in this case, we have coefficients that are defined by the measurements, defined by the basis of your embedding and the unitaries, but the frequencies will be fixed. They will just come from eigen frequencies and gaps of your embedding. And here is the probably the main representation of Fourier feature maps, saying that f of x can be represented as partial Fourier series, whereas omega belong to this collection of frequency gaps, and those gaps will be defined by eigenvalues of your embedding. So the corresponding spectrum will have several properties that we can track, which is the size of this spectrum and its degree. So degree is just the largest frequency, and the size will correspond to how many frequencies do we have. For instance, if we need to fit just a simple sine function, we could upload the rotation x and represent it exactly if we adjust the frequency. We could also re-upload it several times and get a higher frequency signal. And if we do need these higher frequencies, our model will be expressive enough to build it. So the question that for me was very important to figure out is that, can we deviate from the Fourier basis? Why? Because if we just work with Fourier series, partial Fourier series, limited in frequencies, Similarly, we can reproduce them classically. So where does advantage coming from? If you can have a good classical proxy to these models. So the question was, what are the embeddings that give us advantage, and can they have exponential capacity? And I will introduce capacity as maybe not a conventional notion in quantum machine learning, but I believe that's important to distinguish. So when I say capacity, it means the number of frequencies, so and a degree of the spectrum that can be used in principle. So when you derive the model and say its f of x can be represented in certain way, you don't know the coefficients yet, but you know the frequencies. And in principle, you are capable of using all of that frequencies. In practice, though, the expressivity may be very different from capacity. So the fact that you have a high frequency component doesn't mean that you can express models that are oscillatoric, because the associated coefficients will be limited. So on the right, we have the coefficient distribution analyzed in the Schul et al. Paper. And you could see that high frequency components of C5 will have a very limited space to play around. And we also can connect it to trainability. Is it even possible to discover one of the configurations, let's say from C1 and C2, that fit the model? So if we use these definitions, we could probably say that quantum models can have very high capacity. Why? Because I can, in principle, re-upload the gates. I can do it in parallel, and I can tailor my spectrum to have exponential scaling. Making models expressive is not always easy, because in that case, accessing all possible coefficients, you will need to have a very tailored ansatz, and trainability becomes a problem. You have models that can, in principle, have exponential capacity, but how do you find the circuits that actually utilize this capacity? That is not trivial, and of course, that's an open challenge for the field. How can we make them trainable by introducing symmetries, yet not trivializing our models? There is one more possible advantage of QML, and that was pioneered in Berlin. That's generalization. So the ability to learn from just few samples is can be seen as very important advantage, because if you generalize well, then you could, in principle, spend much smaller computational resources while training. That gives you an advantage. And there is a sampling advantage. Why? Because if you prepare your models as a, let's say, quasi-probability distribution, you could sample directly from that distribution. And that's exactly how quantum supremacy experiments are done. So in this case, we have advantage by inverting the PDFs directly on a quantum computer, which is much better than doing it classically. So the high capacity of quantum models and ability to sample, this is the two advantages I will try to describe in this presentation. And the open question is, how do we build these models that can express complex functions, but we can also sample from those functions? So in this case, I will return back to the question of solving differential equations and explain historically how did we come to generative modeling. Essentially, there was a question from some of collaborators working in financial sector asking, so can you solve also stochastic differential equations with those approaches based on quantum neural networks? And it's not a trivial question, because when you look at stochastic differential equation, you need to represent the stochastic variable x in principle as a function of time, and you have a noise term. So how do you deal with SDEs in a classical case? You will need to use some scheme like Euler-Maruyama and propagate many trajectories and average over those trajectories. But you could also say that I am in principle interested in the Fokker-Planck equation. So that will be equation for the probability distribution corresponding to this SDE. And in this case, you can read out observables, but if you want to read out a sample, you first need to integrate a PDF to get the cumulative distribution function and then invert it, which is a complicated procedure. So that's not something you would like to do. We have came up with a different idea, which is to use quantile mechanics. So quantile function is literally an inverse function of the CDF, and turns out it obeys certain differential equation. So if you are able to learn this quantile function and get the satisfy these conditions, any random sample fed into QZ will become a sample from the distribution. So if you have the functions in here on the left and you sample uniformly between -1 and 1, the corresponding histograms will give you the normal distribution. So this way we, for instance, can solve Ursten-Uhlenbeck process. And that was fine and working, but there were a number of drawbacks. So what we have seen that here we still need to evaluate our models at many grid points. To differentiate, we'll need to use a parameter shift rule. So that's kind of a drawback as well. You increase the number of repetitions, but most importantly, that you have the models that are not natively sampleable. So you will need to get a sample as an average from the QNN, which is, of course, not the same that happens in experiments from boson sampling to just supremacy experiments. So in the last few years, we have tried to solve this problem, and what's required here is to build specific feature maps that would allow simultaneously models to be differentiable and sampleable. We also thought about ways to speeding up differentiation, for instance, LCU-based techniques for differentiated models, coming up with new latent space representations of models, and of course, to make them trainable, we will need to deviate from just variational approaches, for instance, implying some imaginary time evolution. So these are all the questions we have considered for ourselves some time ago, and I will be presenting results for each of these points in the following. So let's look first into the question of sampling. And for that, I would like to just describe a feature map that, even though it's extremely simple, it still has the exponential capacity. So imagine that you have a sequence of rotations, RZ. They are parameterized by x, but the denominator goes with this exponential 2 to the power of j that changes from qubit to qubit. And we have been working with those models, which we call a tower feature map, but this is a very specific kind of tower, because if you write a state, the frequencies that appear in front will go just as integers of 2 pi divided by 2 to the power of n. And you have these frequencies. You can build a model f of x with exponential scaling of a maximal degree with the number of qubits. So they're exponentially capable, and they generate the set of orthogonal Fourier states. So the nice feature of such a map is that you could easily come from the Fourier space that we have just built to the computational basis space. And that will be done by the quantum Fourier transform. The very important property of this basis is it's orthonormal. As long as you have orthonormality, you could have a bijective mapping between the two bases. So very quickly, we can recall what is the Fourier transform. We have the corresponding discrete Fourier transform matrix. We could just act with it on the bit string J and get the corresponding frequency state. And that will look like the state that we have already prepared. We only use Hadamard's and controlled rotations to prepare those states. We could also revert the process. We just say, here is the Fourier representation, the frequency state. Let's map it back to the bit basis state. And that is done by a fixed circuit. What is also possible to do is to prepare the state in the frequency space and then modify its composition. For instance, we could prepare the state and then mix it up with other states, so build a model in the frequency space. Only then we perform the inverse quantum Fourier transform and get the readout in computational basis, which can correspond to superposition of states. So in this case, we are really working with amplitudes of quantum states, but the models that we build will now rely on frequencies rather than coefficients in front of each bit basis. And this combination between bit basis and computation and frequency space can be utilized for generative modeling. So specifically, we say the generative modeling follows the conventional route is to follow quantum circuit Born machine sampling. So you have a state psi theta, you have the bit string x, and you say the probability of reading out x is just an overlap squared between these two states. What was missing here for us is the differentiability part. So you say, I cannot really take a derivative with respect to x, which is crucial when you try to solve differential equations. And if you were to do it by finite differentiation, you would need a very fine grid to make it meaningful. So we try to generalize it, and we say the idea is to first apply the feature map u phi of x with exponentially many states. Then you train the model, and in principle, you can see it as reading out some cost measurement operator that leads to the p tilde theta and t. So in this case, we have trained our model in the frequency space. We have fixed the angles. Now we take the optimal angles, we apply it to the initial state, and we also transform it to the bit basis. And in this case, we will be reading out the samples from exactly the same distribution if we were to train it successfully. So this correspondence between training and sampling is really about building models in the frequency space and then transforming it to a bit basis and sampling later. But the good news that in frequency space, we can differentiate and solve different problems. What is also important that if you act in the large, the model has large number of frequencies, of course, trainability will be a problem. But you have an opportunity to limit it to low frequencies, and now you can extrapolate, or rather interpolate between points for a larger number of qubits. Because even if I have a model that's based on, let's say, 20 frequencies that is sufficient for many distributions, I can now apply inverse quantum Fourier transform involving other qubits and, for instance, 20 qubits, and I will have a very fine grid sampler. So that's a simple idea, but that can be applied for some problems. And we tried it again for Ursten-Uhlenbeck process. We had the Fourier-Planck equation that corresponds to this process. We trained the probability distribution just based on data, so more like a regression, and check that derivatives are not matching well here. But you could also train it with physics-informed approach, include the derivatives, regularize it, and also have a fine sampling, let's say with 10 qubits instead of 6 on which you trained. So that was one approach that we have seen working. And we asked the question, okay, so it kind of works, but how is it different from what was done before? And the simple explanation is that instead of using implicit training of probability distribution based on sampling and asking, how do I fit the samples from the QCBM to the data samples? How are they different with this MMD type loss? Now we build explicit probability distributions. And of course, you don't want just to draw some curves. I mean, this is a probability distribution. You won't be able to plot it at every point, but having the constraints on these different probability distributions from the Fourier-Planck plus some data can help training. And there is another kind of important message that we can send, that if you try to train your model based on the expectation value, or let's say probability of seeing some bit string as a scalar, you have one set of parameters, or rather models, where this question can be answered in polynomial time. So the model is classically tractable, just training P of X. But as you transition into sampling regime, if you want to read out samples from that distribution, it becomes sharp P. So the complexity is different, and it becomes sharp in sharp P class, so that you have distributions that are probably hard to sample. And we try to identify such a regime. So in this case, we were looking into instantaneous quantum polynomial circuits, where we say the mixture of Hadamard's and Z operators, also related to the correlation problem, cannot be sampled after the depth of 2, yet you could still read out this overlap. Classically, you can calculate it with tensor network approaches. And then we thought, okay, what we could do is just figure out the circuit structure where it will be showing the favorable properties, like we can read out the overlaps efficiently, but we cannot sample based on criteria of anti-concentration and cross-entropy. And if everything works, we don't need to train it on the device, yet we could deploy it later and show the hardness of sampling. So that's a nice idea. Of course, the question is whether the models are expressive, what can you solve? So still a lot of work to do, but that's one opportunity for avoiding the costly training of generative models. And finally, as we go from the question of what was how can I do generative modeling with Fourier models, we asked, are there any different bases that we could use? Specifically, we have been working a lot with the Chebyshev basis before, because that's for a small number of terms that already gives you nice approximations to many models. So can we build, for instance, a Chebyshev feature map with similar properties? And it needs to be orthonormal. The answer is yes, because you could build your states based on the orthonormality condition of Chebyshev polynomials at the specific nodes. So you say, instead of the Fourier components e to the power of I phi x, I will have the Chebyshev polynomials and of different degree in front of the bit string. I make sure that my state is normalized at for the same x, and the overlap vanishes for different points. It will be non-zero between points, and you will need to keep track of normalization condition if you are in between those points. And just a reminder, Chebyshev polynomial is something that can be represented as a cosine of k r cosine x, where k is a degree of polynomial, and intuitively that will combine the terms that involve two exponents with different phases. So how are we going to introduce this quantum feature map? We will first apply the phase feature map, so e to the power of ix, that prepares the state, and we will try to undo part of the transformation, but in the controlled way. So we say Hadamard on the ancilla, we will rotate part of our state back. We will interfere exponent and minus exponent, and we will scale the rotation such that it reproduces r cosine of x. So in total, we can have the Chebyshev state out. And in this case, we present the first example of embedding based on linear combination of unitaries. So we have prepared the states, we interfere them, collapse on the ancilla such that at the Chebyshev node we get exactly the state. If we do not collapse, it will be superposition of two sectors, but reading out the model in the end, you will you can actually post-select on 0 anyway. And once we have built this feature map, we also want to map bit strings to Chebyshev states and back. So for that, we need quantum Chebyshev transform. It is possible. It's not particularly easy circuit, but that becomes a combination of the quantum Fourier transform on the extended register and some extra phase rotations and conditional operations that you need to add. So the intuition comes from the discrete cosine transforms that it is possible to build from the QFT and some additions. And that's exactly what's needed to map between the bases. So in principle, we see the quantum Chebyshev transform being useful even beyond just quantum machine learning, because one can ask, how do you build models that are non-Fourier? And that's exactly what you need to do. There is also a specific use case that we had in mind, which is the parallel grid evaluation. So not really parallel, but based on overlapping states in Chebyshev basis that's exponentially large, and I will present it in a few slides from now. So few examples how this can be used. You got the Chebyshev feature map, you apply the adjustable circuit, and you train your probability distribution, for instance, log normal. So same story as before, we revert the circuit, we apply quantum Chebyshev transform, we sample from that, and we read out samples from the same distribution, but now each time we read out will be the genuine sample. And you could see it's much easier to work with distributions that are natively presented by Chebyshevs rather than Fourier. For instance, the linear distribution, it will avoid oscillations that Fourier will inevitably have. And the next step for us will be to use these models for solving differential equations in the latent space. So it's presented in the work with Annie and Vincent. We tried to explain in the best possible way. It's not particularly easy, but let me just try to do it in 30 seconds. So the idea is to have differential equation terms and the model f of x that overlaps the state with the state f of theta with the state x. And I don't yet specify the basis, but that's just a projection on specific state. We say this state can be represented by a set of Chebyshev polynomials. So you ask, what is a proportion of f of theta that has a specific fraction of a Chebyshev polynomial? And the overlap does not have absolute value squared. So we really need to measure the overlap between two states that in principle can be complex, but we require it to be real. So if the basis is orthonormal, we could check whether the differential constraints are satisfied by checking overlaps between different states. And we say there are concepts that represent the function itself, the derivative, the square of the function if we extend the register, and based on evaluating how far away the states are, we assign this a certain loss. And the idea for solving differential equation is just to minimize the distance between those functions. So here we don't rely on evaluating function at every point, but rather we check that in this spectral domain, do we have the same coefficients for functions and derivatives? If we do, we have solved specific equation. And we got this idea for Chebyshev, also working for Fourier, but we could apply it for many other feature maps if they have this orthogonality property. And we could also build it in multiple dimensions that would require some circuits to extend it, but okay, these are the technical details. And we have also shown that in principle, you could solve linear and nonlinear models if you introduce multiplication circuits in the Chebyshev basis, which is very nice because multiplication of Chebyshev polynomials is another Chebyshev polynomial, so you don't need to extend your space much more than just with one extra qubit. Okay, so that was the story how to use it for differential equations. Now let's also ask a question, can we extend our basis? And we have thought about the simplest possible modification, which is the Hartley kernel. So instead of implementing the exponent, we could build the basis based on cosine and sine function that is also orthonormal, and which is known as a Hartley kernel function. So in this case, we have a similar feature map. We don't need the extra scaling and phase factors. We can use the same approach for training, get the distributions out as some curves, and the good part of these models that the models are real valued, so there is no complex part, and they will fit better to some problems. We can also build a quantum Hartley transform circuit to map between the states and use it for sampling also in a larger space. And in our research so far, we seen examples where Hartley models were working better, let's say, than Fourier and better than Chebyshev. So it has its own place in the pipeline of generative modeling and differential equations. Specifically, what I want to stress that if you introduce this physics-informed training and you want to build f of x as some probability distribution, sure, you can do it, but what you want to do is sampling from a multivariate distribution. So you don't want just to have a single distribution of P of X, but rather a P of X, which is a vector. And we have tried it for bivariate functions. We take two feature maps. We introduce a correlation circuit that will link the registers, and we also have the basis adjusting each distribution individually. So here as a result, we can reproduce the bivariate normal distributions with strongly correlated variables, and we could go all the way from zero correlations to positive or negative correlations. So where do we see advantage in the end? It's not about just fitting some probability distribution for a single variable, but rather finding the conditions where we can have many distributions that each marginal will be simple. We know how to reproduce it, but correlations in between the distributions will make it difficult to sample, even if you use state-of-the-art tensor train approaches. Okay, and that was the story about generative modeling. I will just ask for questions now, and in the next maybe 5 to 10 minutes, I will go into classical versus quantum data.
Yeah, in the meantime, Jens made it, so we have now Jens in the big room.
Yeah, sorry. I mean, I was in the call anyway, but now I'm physically here. Oh. Okay, better?
Yeah.
Ah, I see. Sorry. Wonderful. That's very interesting. I have maybe a high-level question on the point of sampling and readout that you mentioned earlier. I mean, like, how surprising is it that there are some setups like tensor network based so that you can efficiently model expectation values, but sampling is hard? Because you seem to have examples of that type. I mean, there's many examples of that type. Say if you have a 2D lattice, you can just think of a unit depth circuit that gives rise to a tensor network of 1 dimension 2, where you can compute everything exactly efficiently just by conjugation. But you also cannot efficiently sample from that up to a constant error the toleration distance. So are your problems like of that type, that you have like some like hardness claim based on anti-concentration and so on, but you can still efficiently contract the tensor networks? Is that what you had in mind?
Yes, exactly.
I see.
So I should say that's where we aim to be if we want to avoid training on a quantum device, because if you were to use like 1,000 epochs, it's not going to scale for quantum hardware, especially if you need to differentiate. But if you have a tensor network proxy to the overlap that is computable, you say, I have trained these models, it's still polynomial, even though we don't know the power, but let's say it's manageable. Now let's sample from that distribution, and that becomes hard. So
I see. Okay, that's okay. I got it right. And another, like, it's not really a question, but it's more like a comment. And there's also a comment to everybody here locally in the team, which is but that's the point in what I say, which is that it seems so much easier to find like separations from quantum to classical based on sampling compared to expectation values. I mean, you know, all these supremacy / quantum advantage setting based on random circuit sampling and so on. But now in the context of training and so on, I mean, I have seen little progress on using samples in training where there could be an advantage in using the samples directly from the quantum device compared to using expectation values. Yeah, so I mean, of course, there's work on like training quantum circuits based on like n-shot data, and we've even published ourselves about this. But this is like more of the time we would want expectation values, and we just do single shot like estimators thereof, which is great, but we have not made use of the intrinsic randomness as a resource. And that might be an interesting idea. And what we hear this nice talk is a bit in this direction, but not the full thing yet, but it might be worth thinking more about.
So yeah, I can comment on the sampling part. So when we discuss the training, we say the implicit models like QCBMs, you just read out samples and that's it. You have collapse and certain outcome, and from there you will build your probability distribution. But when we have this transformation, we have access to the explicit model, but we could still use samples as a data to satisfy. You just need to change the basis. And it's possible to do simultaneously when you train. So this idea of reusing some part of your experiment or something that you got a knowledge of samples, plus some physics-informed, let's say, behavior of your distribution should make models generalizable, so you could generalize easier. That's at least the intuition. And we have partially seen it for some distributions where you can postulate that, oh, I will obey a certain differential equation, so I roughly learn the curve, and the rest I learn from samples. That works, but again, it's also relies on whether the circuits are trainable. So you need to restrict your variational ansatz as well.
Is there time for another short question, or is that illegal?
Yes, please.
I also like your DQCs for generative modeling and your stochastic differential equation ansatz to generate samples. That's really cute, and that relates also this kind of learning business to solving differential equations. I was wondering to what extent, sorry, that's a bit of a stupid question, but I mean, that you made this kind of Wiener noise ansatz, like something plus Ito calculus Wiener noise term. I mean, how much is that set in stone? I mean, are there other unravelings like based on jump processes or so, or is there a rationale behind your diffusion type setting? Or is that just a stupid question you want to say, shut up and stop the question?
The Wiener process really comes from just how it's usually treated in stochastic differential equations. There are different types of noise.
Yes.
With, for instance, colored noise, they will just lead to the different types of Fokker-Planck equation, which you could still try to solve.
I see.
And
but that's this kind of classification of stochastic differential equations, right? I mean, they're all the concatenation of deterministic, Wiener noise, continuous stochastic, continuous stochastic, or of a jump type interrupted by deterministic equations. I think that's all there is for Markovian stochastic differential equations. I'm just wondering, is there a point in jumps as well, or is that not interesting?
So initially we have thought about whether trajectories can be represented as some actual quantum noise process.
Yes.
But we gave up on that idea. I don't know, maybe it's still possible, but we just said, okay, let's mimic what is done classically, but the probability distribution will be substituted by the quasi-probability distribution, which is a wave function. So in this sense...
Okay. Then I see your mindset. Okay, I think I see where you're coming from. Thank you very much.
Okay, great. So let's then proceed to this question of quantum versus classical data. So when we say data is classical, we imagine some either images or voice or text or whatever. But when we talk about quantum data, we say this is a density operator, a configuration of spins on a lattice, so something that can come from either experiments, some sensors, or just prepared in the lab. And there was a strong distinction between these two classical and quantum data settings when you learn, and quantum seems to fit much better the QML part. But for me, it was kind of difficult to understand why would it be so different and what's special about quantum data. So that's the question we ask: can we formalize this approach, and can we bridge the gap to what was known before? For that, we say, okay, I want to do the quantum convolutional neural network. So I take a state raw, I perform some basis transformation measurement, and I get the observable that classifies a phase. For instance, is this state in class A or B? So topologically non-trivial or trivial. And the data here is dependent on some parameter X. For instance, it's the strength of cluster interaction, which we say in the end represents our data. It's a physical process that parameterizes your Hamiltonian, and based on that value of the parameter, you got the quantum representation, which is a state. And from that state, you can distill some useful properties. So how do these states appear? They come with a quantum process of either ground state preparation or some dynamical process, but that's your feature map. And this is a very specific feature map. It's not based on rotations or LCU or anything, but that's how nature prepares the quantum data. And we would like to understand how the X dependence of these input states actually underpins the basis and what are the models. So we take the transverse spin 1/2 cluster Hamiltonian that has this 3 body term and the X and Z basis rotations. We say that X will be a parameter in front of the cluster Hamiltonian, and we plot the basis functions as simply just projection on the bit basis. What we see, and that shouldn't be surprising, that our basis states, the amplitudes, have a critical point at the transition between clusters, ground state, and the trivial ground state, which is spin polarized. And we also can combine basis functions into the combinations that would have this sharp boundary transition. So we say that from the point of view of data loading, the ground state prepared for this model fits perfectly this sharp boundary in the critical point. And that's what we, in the end, need to do. So the Iris Kong and colleagues have presented this QCNN, extremely powerful technique, and they said we can have a fixed circuit that exactly solves the problem, and we can variationally extend it to be even better. That's what we try to reproduce. We take the cluster Hamiltonian, we apply the pivot rotation to make it trivial, then do the checks with Toffoli's, pivot again, and in the end we measure just a single qubit. And if we do it for 1, 3, and 9 qubits, we see that decision boundary becomes sharper and sharper. And the reason is hidden in the QCNN basis, because the basis functions are all having these sharp transitions in the middle. So it's quite, you don't really oscillate in between, you actually have a sharp boundary. And we check it variationally. We say, instead of just fixed circuit, we could ask, can we learn the boundary? And indeed we can, even for a very limited number of iterations. So for just 10 iterations, the accuracy was 42%, but it grows up to 100 when we have 75 or more iterations. So these are the models that can be trained. And that comes to the statement that QCNNs are trainable. We have also checked that how much can you outperform the Fourier models, because Fourier models can fit many functions, so that's not a problem. And we see even with oscillating Fourier function, you still can have the 99% of accuracy. So you add rotations, you can draw decision boundary at 0, and that's in principle gives you some separation. However, as you consider the finite number of shots, that becomes difficult. It becomes difficult to generalize, because these Fourier methods, even though for ideal sampling you have the separation, it has a large variance, and instead ground state embedding will have the very clear decision boundary. So for a small number of shots, we still get nearly 100% generalization. And that comes to a question, how do we understand the ground state embeddings? Are they based on low frequencies or high frequencies? How does this process happen at all? And can we also use similar approach to regression? So I'll skip this part, just saying that we have tried to use QCNNs for regressions for the critical phenomena. It works, it doesn't oscillate, but you need to find specific use cases for that. And the part I would like to concentrate is connecting ground state feature maps with Fourier models, and from the fundamental point of view. And the way we decided to connect it is to select the ground state preparation, make it x-dependent, so some parameter of the Hamiltonian, and analyze it by the standard Fourier decomposition approach. The imaginary time evolution of variational preparation doesn't really work here because you cannot easily write a Fourier model. What works is taking the adiabatic state preparation and trotterizing it, because in this case you have access to frequencies with many reuploadings. And that's what we did. We took the Hamiltonian that follows an adiabatic path. We arrived to the ground state of H1x, which is, let's say, a cluster Hamiltonian or Eisen model Hamiltonian. And we take this unitary as a time-ordered exponent. We trotterize it in steps. We consider the different steps, but making sure that the quality of solution is sufficient, and we expand it into Fourier series. So formally, it's a sequence of steps where you split it into separate unitaries, you transform the basis, you read out your eigenvalues, you form the gaps, and you know the spectrum, its size and degree for the underlying model. And the interesting part is when you take the simplest longitudinal transverse Eisen Hamiltonian and check, let's say, magnetization, you see phase transition at the point here, x equal 2. So you could represent it with this adiabatically prepared state. You could also check the fidelity. So are we in the ideal state prepared by from exact diagonalization or not, and make sure that the t, the maximal propagation time, is sufficient to have a good approximation. And what we discover that, of course, at the critical point, the time to have to reach a high fidelity of 1 needs to increase significantly. So even for t equal 1000 in units of Eisen interaction becomes too long. So what we find that fidelity as a function of the number of steps also requires very large number. So you really want M to go over 10,000 steps to reproduce this ground state. And if you look at the basis functions for the adiabatic and exact state, we still recover the sharp phase transition for the exact ground states. But in the adiabatic case, we start seeing very high oscillatory accretion in the critical at the critical point. So what it suggested to us that when you do this ground state embedding, you can represent it as a Fourier model, sure, but this Fourier model contains extremely high frequency terms, and the basis functions work such that these terms have a destructive interference for high oscillatoric terms and constructive for these sharp transitions. And unless you go adiabatically, you will never fully recover those bases. So we have quantum models that have large number of reuploadings. They're based on high frequencies, and the interference between those terms leads to a smooth and regularized basis. So that's a formal statement. Our mode spectrum, if we plot it for the Fourier map, so that's at the top, we'll have frequencies that grow with the system size, and the number of counts, so the degeneracy, will be gigantic. So even for few qubits, we observe it grows up nearly to 1 million of frequencies. At the same time, rotational feature maps will have only few coefficients per frequency, and the degree will grow slowly. So what we can conclude that models based on quantum data are of the high frequency type, but they are fitted for the specific purpose. And this can be also supported by seeing what are the coefficients of those models. We see that coefficients, when we load, have very high proportion of low frequency coefficients. They also have some high frequency coefficients, but the distribution is kind of colored. So you say, I will prefer certain frequencies and not others, and that leads to the smooth behavior at the critical point. And I believe it's still a lot of work to do here, but what we shall try to understand is how do we come up with feature maps that are suitable for a specific problem and that have expressivity that just enough to solve them. And in this case, we should be able to develop the embeddings and do the minimal variational part, or maybe no variational part whatsoever, and still solve the QML problem. So, okay, I believe in the interest of time, I should skip the story about the geometric quantum machine learning part, and I will just conclude saying that quantum embeddings so far were mostly based on rotations, so just applying rotations, reuploadings, and building Fourier models, and amplitude-based encodings. We could say that amplitude-based encoding is just a specific frequency encoding that can be linked by the map, and we have the control now of the spectrum and how to map it to the bit strings for doing generative modeling. We have a linear combination of unitaries encodings that do not follow Fourier because you will interfere different exponents, and that can be arranged as Chebyshev or Hartley basis. And we also have ground state feature maps. So something that can be prepared, and we know that underlying spectrum is rich and is actually suitable for solving some problems, for instance, classification of phases. And the question is, what else can we do? Which other embeddings can we have for expressive and trainable quantum models? So with this, I come to my conclusion that still a lot of things to do, but quantum machine learning was developing, and specifically for solving generative modeling problems and scientific machine learning, we expect that at a certain point with tailored models and let's say advantage from sampling, we can start to challenge state of the art in classical case. Thank you for attention.
Thanks. Thank you very much. This is very, very good and insightful. Do we have any questions? Right away. I would have a question on like the perspective, like in this like the slide just before this one, you listed the three big building blocks with which we can embed classical data. It would be like rotations and the amplitude, which would be the type of rotations, then doing this nonlinear transformations of amplitudes. That like this is also in my head what people talk about in this QSVTs and qubitization and these things. It's like applying this nonlinear transformations of the unitaries with which then you can fit other types of polynomials. And then the ground state one, even though you mentioned that if you think about how to implement it in practice on a quantum computer, chances are you would end up doing factorization, which could even be seen as some special case of rotations again. And this is what you showed that the high Fourier modes would do mean stuff at the first transition. And I really like how you presented all of them together. My question, which is like perspectives, when there is practical quantum advantage in learning with PQCs, like when this quantum circuits beat neural networks at something, do you have any gut feeling for which of this would be the one that gives this advantage?
So the intuition, I guess, so the best shot, I believe, is when you need to sample, because otherwise just drawing functions, like drawing curves, that's not what we can easily do from the state with exponential number of frequencies. If we reduce it to expectation value, that's much easier to simulate classically. So my feeling is that it needs to be the representing probability distributions and solving the task from sampling. So let's say augmenting the data sets. And second, it needs to be multivariate, because I looked for many problems in generative modeling, financial analysis. There are no examples where a univariate probability distribution can be sampled. And sure, you could say let's say random sampling problem represents a highly non-trivial probability distribution that's difficult to sample, but in practice for a real world problem, you never see it.
And I think I agree with what you said. What you said, that drawing a curve is easy to do classically, this natively talks about the regression problem. Would you think that then the step from this curve to like the classification of that you have a bunch of these curves and you take the maximum, that would not change things? Would that still be like your intuition? So that would still, it would still be difficult for a quantum model to be better at a classification task.
So with quantum data is slightly different, I believe, because the model in the end would look simple, yeah. So the bound, the decision boundary is always something kind of a step function. You will never need for the highly oscillatoric function in that case, but it's important to generalize well, and quantum models will have this generalization coming from the basis already supplied by the states on which you train, which for classical models may be difficult, because you will just read out certain observables, moments, and you will try to build your model on the measurements rather on the state itself. So in that case, we could say it's not about sampling like extra samples, but using the smallest number of samples to learn. So generalization advantage.
Nice. Yeah, that's a very good perspective. Thank you.
Can I use the opportunity to ask a completely off-topic question?
Yeah.
The great talk, by the way. I really enjoyed it. So you talked about quantum data at the end, and indeed there's some evidence that quantum data make our life easier compared to classical data, and you've also given further hints on this. What's less developed, to my understanding, is to use quantum training for classical data. And we have a bit of work in this direction, like when we earlier this year had a paper on like quantum training of sparse prune large-scale classical networks, which is kind of cute because it gives a new perspective and it's usable for very practical classical data. But this is not a field that's much developed, and I wonder why. And in your kind of big ride through the field that you presented today, like why is the quantum training for classical data, classical networks missing? And do you have ideas about this? Or is this crazy? Again.
I don't think it is crazy. I just believe it's hard.
Okay.
So you need to come up with good arguments, maybe from statistical theory, why loading a lot of classical data into quantum circuits will lead to advantage. But no, I believe it is possible. It's kind of it's known that you could take classical probability distributions. For instance, in Google's learning from experiments case, they take classical probability distribution and they show advantage on, let's say, analyzing or predicting something about classical probability distribution. So it should be possible to learn on classical data, but it's just probably hard conceptually.
Okay, fair enough. Thanks. And nice talk, really nice.
Thank you.
Yeah, I mean, just one final mini question on this. So relating to what you said, that the advantage of quantum machine learning in generative modeling requires that it's like high dimensional distributions. And I assume that they have to be far from product, of course, otherwise they're not really high dimensional. And yeah, like I think mostly about the classification tasks for classical data. Like that's the thing that comes to my mind when I think about these things. I'm trying to think what sort of data you would need, classical data, like images of cats and dogs, but where like images of cats and dogs, you have only like local correlations, for example, and like they are mostly two-dimensional because they're images. Like, would you have an idea how a classical data set should be in terms of dimensionality and correlations, such that we could hope to have like good performance from quantum models? So it's okay. Again, your gut feeling.
I think it is difficult to answer because I could say, let's look for temporal correlations.
Mm-hmm.
If I take a data set that's not just vowels where correlations are local in time, yeah, I mean, you don't need to track too many points before and after. In financial analysis or some signal processing, you want to get information about the history, like so you want to develop these correlations. What's missing is the clever way of embedding those.
Mm-hmm.
Because saying that quantum is good for some correlations, long-range correlations, doesn't mean that when we load a data set, we maintain these correlations in a specific way, and then we process them in a way that we really work with those correlations. In most cases, we would kind of load the correlated data and destroy it. One case is I worked on the fraud detection as well, and we were taking features that in principle can be highly correlated. But if you do PCA to that data set, principal components are not correlated anymore.
Mm-hmm.
So getting the quantum advantage there is difficult. So it's about a smart way of loading it and processing.
Mm-hmm.
And possibly with equivariant approaches and with geometric quantum machine learning, you could still do it.
Yeah. Okay, cool. Very good.
Cool, nice.
Okay, then thank you
Wonderful.
very, very much.
Yeah, that was super insightful. Thank you so much.